Then go your room. We in class now. Go your room. But I'm in class. Go your room. Why? Just go your room.
Okay, let's get started. So this will be a two-part lecture, so I'll cover this over 2 days. On chapter 4 material, this is talking about some basic physics that goes into understanding things like planetary orbits, and we'll use this throughout the course though. It'll apply to all sorts of things. So we're talking about motion, concept of energy in all of its forms, gravitation. Okay, we haven't actually talked about gravitation much because, right, we talked about these old ideas about planets orbiting on crystalline spheres, right, around the Earth. Okay, but the modern view that we're going to understand is why do the planets orbit, right? What causes all of that? And actually, it all comes down to some very simple rules, basically discovered by Newton, that things gravitate towards one another. And from that, you can derive everything else, including Kepler's laws. Are there any questions before we get started? Remember, you have a homework due today on mastering astronomy, and a quiz this week, quiz number 2 on D2L. Okay, so motion, right? We want to understand some of the basics about how to talk about Newton's laws. And in order to do that, we need to talk about motion, like what is speed, okay? Speed, if you drive in a car, right, you have this speed meter in there, right? Kilometers per hour or miles per hour. It's distance traveled per time. So some distance every some amount of time. Okay, distance could be measured in meters, or miles, or kilometers. Time could be measured in seconds or minutes. So it's how far you go per given amount of time. So speed of a car might be 60 miles per hour. So that's 60 miles you travel for every hour, which is the same thing as 120 miles, so twice 60 over 2 hours, twice an hour, or 30 miles every half an hour. You'll see that those ratios are always the same, okay? 15 miles every quarter of an hour. Okay, so that's a speed. And the units of speed are distance per time. So meters per second, miles per hour, kilometers per hour. And if you just kind of turn that around, if speed is distance per unit time, well, that's the same thing as saying that distance is speed times time. That is, if you know how fast you're going, say 60 miles an hour, well, if you wait an hour, you've gone 60 miles. So distance traveled is speed times time. So for example, here's a calculation, the sort of thing you might do if you're on a road trip. Okay, so suppose you're on a highway, you travel 162 and a half miles, and it took you 2.5 hours. What speed were you going? Well, you have a distance, you have a time. So the change in distance was 162 and a half miles. The amount of time elapsed, the change in time was 2.5 hours. So you just divide the two. 162 and a half miles divided by 2.5 hours is 65 miles per hour. So you're going 65 miles for each hour that you travel. Now, in physics, we have a different word for velocity. Velocity and speed do not mean the same thing. Okay, velocity is the rate of change of position of an object. Okay, and at first that might sound like the same as speed, but velocity includes direction. So it's the rate of change in position depends on the direction. So the velocity tells us both the speed and the direction. So an example of velocity would include a speed and a direction, like 30 miles an hour north. Okay, that would now be a velocity. Or 100 miles an hour northeast. Okay, those are examples of velocities. And in order for a velocity to change, two things then could happen. It could be either the speed changes, or actually the speed could remain the same, and it could just be the direction of the velocity changes. That still causes the velocity to change, since the velocity includes the direction. So a really important example here is circular motion. So if you have a car, for example, on a circular racetrack, and it's at constant speed, so say it's 100 miles per hour, and that speed isn't changing, but as it moves along the racetrack, here are two examples. Here the velocity is pointing to the upper right, but you wait a second, now it's over here. Now the velocity is down to the lower right. So the velocity is changing, okay? So it has a changing velocity even though the speed is constant. Okay? That's a good example really showing the difference between speed and velocity. And to really drive the point home, here's an example where we could work through, what is the change in velocity? If say you start out, you're going around a circular track, and we imagine a car is at point A, so it's going south, and then a few minutes later or seconds later, it's gone halfway around the racetrack and it's going north. Okay. What is the change in velocity going from A to B? Okay. So we're going to need both a speed and a direction. How much the speed changed and or the direction. Okay. So what is the total change? Well, the way we figure out that is we take the velocity at A, we take the final velocity at B, and we subtract. We find the difference between that and the initial velocity at A. So what was the final velocity? Well, the final velocity was 10 miles per hour north. Okay. So we take 10 miles per hour north and we subtract 10 miles per hour south. How do you subtract 10 miles per hour south from 10 miles per hour north? Well, to go south is the same as going north in the negative direction. So 10 miles per hour south is the same as minus 10 miles per hour north. In that way, we have 10 minus minus, the two minuses become plus, and we get 10 plus 10 is 20 miles per hour north. So in this example, the change in velocity was 20 miles per hour north. In other words, to go from going 10 miles per hour south to heading 10 miles per hour north, you had to change by 20 miles per hour in the north direction. You had to turn around. You had to change your velocity in the north direction. Okay, so that's an example of a changing velocity. And that's important. Why do we care about changes in velocity? Because that's what acceleration is. Okay, acceleration is the rate of change of velocity, and you can have an acceleration just by speeding up. Okay, you can be in your car and you just start to speed up. That's an acceleration. Or you could slow down. That's an acceleration in the other direction. Slowing down means to accelerate opposite your direction. Okay. But you could also have a change in velocity by neither speeding up nor slowing down, but changing your direction. Okay. So for example, if you're accelerating perpendicular to velocity, you're going this way, but you're accelerating this way, that's turning. That means you're turning. Okay, so that's an example of accelerating to turn, because even if your speed is staying the same, you're changing your velocity. So acceleration is defined as change in velocity per elapsed time, meaning how many miles per hour are you changing every second? So for example, a unit would be of acceleration might be miles per hour, or meters per second, which we call meters per second squared. So the units are distance per unit time squared. So here's an example of an acceleration. If you're in a car moving around a circular racetrack at constant speed, okay, your velocity is changing. Okay, how is your velocity changing? Well, it's changing towards the middle. So if you're at this point and your velocity is this way to the upper right, how does your velocity change in order to get over here? Well, your velocity had to be shifted in the direction that A is pointing. That purple arrow is pointing towards the center of the circle. So actually, in circular motion, in order to remain at constant speed and go around a circle, you have to constantly be accelerating towards the center of the circle. That's an example of constant acceleration. Well, the acceleration is actually changing. The direction of the acceleration is changing, but the magnitude of the acceleration is constant. It's always pointing towards the middle by some amount in order to keep you turning. So, why do we care about acceleration? Well, things accelerate in gravity. So we're all familiar with on Earth, you drop a ball, it falls. It appears to fall at some rate. In other words, its velocity changes. You hold it still, no velocity, and you let go, suddenly the velocity starts changing. That means it's accelerating, okay? And G is the name we have for the acceleration of all objects on the surface of the Earth. And for a while, people thought that things that are light, things that don't have a lot of mass, don't fall as fast. Whereas heavy things, they are pulled down to the Earth, so they fall faster. Well, Galileo, this guy we talked about last class, who came up with all sorts of great ideas, especially advocating for the Copernican revolution. Well, he did lots of stuff. One thing was making a thought experiment and arguing that, no, actually, it doesn't matter what your mass is. Everything should fall at the same rate on Earth. And the thought experiment is, okay, imagine we have something that's mass m, and then something else that's twice the mass. How can we show that those two things, twice the mass and one mass, have to fall at the same rate? Well, imagine taking that thing that's twice the mass and just connecting, pulling it apart a little bit so it's only connected by a thin string. That's what's shown in this picture here. So you have two bits of mass, but if you just barely connect it together, it becomes one mass. But how is that little connection of string doing anything? How is that causing them to fall any faster? In fact, you could then just separate them completely, and now you have two smaller masses. And no matter, if you think carefully about it, you see that doesn't make sense, that if you take two masses together and you suddenly just barely touch them together, suddenly they're going to start falling faster. So this thought experiment shows that if you take a mass and you divide it into smaller pieces, they all should be falling at the exact same rate. It doesn't matter what mass something is. It should all fall at the same rate. And Galileo was right about this. The reason why it was hard to tell that this was true was because of a complication, which is that there's air resistance in the real world. So if you take a feather, okay, it doesn't fall at the same rate as a bowling ball. Why? Because of this additional complicating factor that's not about gravity, it's due to the air resistance. Air prevents a feather from falling. Okay? Now, in modern days, we can actually test this. So I have a very nice video for you of the world's largest vacuum chamber. We're going to see a test of this. I'm going to play it.
This is NASA's Space Power Facility in Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft and missions in outer space, and does that by pumping out 30 tons of air. Galileo's experiment was simple. It took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. We drop 2 millitorn and last 30 minutes. But once it's complete, there's a near perfect vacuum inside. 6104, gold. Station 1, go for drop. TCD 30-1, pressure set point 240 psi. Here, go for drop. 10, 9, 8, 7, 6, 5, 4. And we're on, 2, 1, release.
Okay, so as you can see, the reality is that if you put something in a vacuum, you remove the air, feathers and bowling balls all fall at the exact same rate. And this has some important consequences when we think about gravity. So first of all, there's a possibly apocryphal story that Galileo actually did this. Of course, he couldn't create a vacuum, but he could drop two, one heavier, one lighter bowling ball and show that if they're heavy enough, air resistance isn't so important. So you can show that they mostly fall at the same rate. And of course, the apocryphal story is that he used the leaning tower of Pisa, because then you can drop it out over the sides and it won't hit the wall. But what this means, though, is that acceleration due to gravity, we don't care about the mass. It's always the same for everything. So we just have one number. And it's different on the moon than on Earth, right? The moon has less gravity than the Earth. But ignoring air resistance, on Earth, acceleration due to gravity is 9.8 meters per second every second. So every second, you gain velocity downward of about 10 meters per second. So we say g is approximately 10 meters per second squared at Earth's surface. So what does this mean? So you drop a ball from, some height. Every second, it gains 10 meters per second. So after 1 second, it's going 10 meters per second downward. After 2 seconds, it's going 20 meters per second downward. After 3 seconds, it's going 30 meters per second downward. Every second, it gains more velocity downward at that same rate. So things fall faster and faster as you wait longer and let them fall faster and faster. Now, keeping in mind, okay, we're ignoring air resistance when we talk about this. Okay. Suppose you were to go to the moon. Okay. I'll ask a question based on what we're talking about. Okay. You go to the moon. And you drop a 10-pound weight and a 5-pound weight. And this is the sort of thing that's actually been done on the moon. Okay. You drop a 10-pound weight, you drop a 5-pound weight, both from the same height at the same time. What will happen?
The heavier. Wait, but I think it's gonna float because it's out in the air.
Maybe 10 more seconds. Okay. All right, so people on average got it right, but a lot of people said both weights will float freely since everything is weightless on the moon. Well, that's not true. I mean, the moon has gravity. It's not as much as the Earth, but things fall on the moon. We all know that. We've seen pictures of people walking on the moon. Things fall towards the moon's surface. But because of what I described here, it doesn't matter what the mass is, whether it's a 5-pound mass, a 10-pound mass, or just a feather, all things will fall at the same rate and therefore hit the ground at the same time on the moon. Any questions so far? By the way, I guess, so they've actually done this sort of thing in Apollo. Here's let's see. The Apollo astronauts.
Then a demonstration of a classic experiment.
The video isn't very good, but.
In my right hand, a hammer. I guess one of the reasons we got here today was because of, long time. happens to be appropriately a falcon feather or a falcon, and I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
It's hard to see, but yeah, they did. They did fall and hit the ground at the same time. And their module that they were riding in was called the Falcon. All right. Next, we have just a couple more terminology things. So we talked about speed and velocity and acceleration. Another really important concept is called momentum. And it's actually just in terms of things we've already learned. So momentum is just mass times velocity. That's all it is. Okay. It's called linear momentum. There's also angular momentum that we'll talk about. But linear momentum, mass times velocity. So if your velocity changes, your momentum changes. Okay. Your mass changes, your momentum changes. Okay. So it has since it's mass times velocity, it has a direction and a magnitude, just like velocity. And since now a force, as we'll see, causes an acceleration, meaning a change in velocity. So if you have a force, you're going to have a change in momentum. Angular momentum is the same thing as momentum, but for rotation. So we'll talk about that in a little bit. But given this, momentum is mass times velocity, you should be able to answer questions like, if you double the velocity of an object, what happens to its momentum? Well, momentum is mass times velocity. Velocity is doubled. Momentum is doubled. Okay. Here's another question just to think about, and I'm going to give you the answer and we'll talk through it. Consider a car driven in a circle at constant speed. Okay. What quantity is not changing? So let's think about this. Well, the position is changing, right? It's moving in a circle. Okay. The velocity is changing, right? We talked about this, that even if you're at a constant speed, if you're moving in a circle, the velocity is changing because the direction of your motion is changing. What about the acceleration? Well, we showed a picture of this. The acceleration is changing because it has to point always towards the inside of the circle. So the acceleration is changing. And if the velocity is changing, as we saw in part B, that means that the momentum also has to be changing. So they're all changing. So the answer to this case is none of the above. Okay, so here we're getting to something cool, which is that we talked about Kepler, right? Kepler's laws, describing the orbits of the planets around the sun, right? Ellipses and all, and he had the rule that said that you get closer to the sun, you go faster, and you slow down further away from the sun. Had the rule talking about how far you are from the sun and how that corresponds to longer and longer years as you get further away from the sun. Well, he never said anything about gravity. Okay, Newton came along and published Newton's laws, three simple laws governing all objects and gravity, saying that everything gravitates, the moon, the earth, the sun, and he derived everything, including Kepler's laws, all from these basic ideas. And it's very beautiful. It's a great simplification in line with this idea of Occam's razor that we talked about in last lecture. So here's just a historical overview. The Copernican revolution was around the 1500s, the beginning of this change in the worldview from geocentrism towards heliocentrism. And some big names were Tycho Brahe, who took meticulous data, Kepler, who came up with Kepler's laws and his geocentric model with orbits, planets following ellipses, Galileo, who argued forcefully for a heliocentric model. Okay, but then just after that, Newton came along, and he really put the final word on all of this and convinced everyone that this was the correct view, because they saw that all of these, the very simple assumption, all matter gravitates towards all other matter. And his three simple laws was able to derive all else. All else just fell out of it. You see that the sun is more massive, so it has more gravity. All the planets orbit the sun. It also explained all sorts of things, like the moon orbits the earth, that otherwise was unexplained. Okay, so he came up with 3 laws of motion. We'll go over those. The law of gravitation. All matter gravitates towards all other matter. In order to do calculations with this his new laws, he had to invent calculus. So you can thank Newton if you've had to take a calculus class. And he also he did all sorts of stuff. I mean, one of them was he invented the first kind of reflecting telescope, which is the kind of telescope that is the most important type of telescope today. Okay? So what are his 3 laws of motion? So all things in the world follow these 3 laws. Law 1 was anticipated by Galileo. An object in motion stays in motion. An object moves at constant velocity if no forces act, meaning you throw a ball in space, there's no forces, it just keeps going in a straight line. You don't have to keep pushing it, in other words, it'll just keep going in a straight line. Okay, that's law 1. Law 2 tells you exactly how much an object's velocity changes with time. In other words, what is its acceleration when it is subject to a force. It's given by F equals ma. Then finally, his 3rd law says that if the sun exerts a force on the earth, for example, well, the earth exerts an equal and opposite force on the sun. Okay, if I exert a force on this table, the table exerts an equal and opposite force on my hand, which is why my hand doesn't just go through this table, it pushes back. Okay, so those are Newton's 3 laws. Let's go through them. So, first law of motion: an object at rest remains at rest. An object in motion remains in motion unless it's acted on by a force. Okay. Object with a constant velocity just keeps coasting at a constant velocity unless there's a force. Okay. Now, if I scoot something across my table, of course it comes to a halt, but that's because it is exerted, a force is exerted on it, friction force. Okay. But if it's not for a force, things just keep going. Okay, that's Newton's first law. Newton's second law allows you to calculate, given a force, how much does an object accelerate, right? Well, it's proportional to the mass. So that's what F equals ma says. You have a force. How much does it accelerate? Well, it depends on the mass. If I exert some force, so that's indicated by green here, so some force on a ping pong ball, and the ping pong ball flies away, it has large acceleration. If I take that same force and apply it to a boulder, something with much larger mass, that boulder hardly moves at all. Okay, same force, smaller acceleration. Okay. That's all explained by F equals ma. Okay, if I increase m, well, if F is constant, a has to be smaller. If I decrease m, so like a ping pong ball, but the force is the same, the acceleration increases. It has to be large. F equals ma. That's all it says. Okay. And since a force causes an acceleration, which is a change in velocity, it means a force also causes a change in momentum. And examples of changes, in accelerations, well, like we talked about, you can speed up if the force is in the same direction as your velocity. So you're coasting along and a force is applied in the same direction as your motion, you speed up. If a force is applied opposite your motion, you slow down. And then the third possibility is you can cause turning. So if you're moving this way and a force is sideways, then you start to turn. That's another example of a changing velocity. So those are examples of F equals ma in action. Another example is, so if F equals ma is all around you, all the time, it's important. It's why you're not falling through the earth right now. It's why anytime you touch something, right, it moves or it pushes, it either accelerates or it doesn't, depending on its mass. And one example that that's really important is why, if you go around a turn on a highway, so here you say you're going a highway on ramp and you're turning, that means you're accelerating. Remember, you're going in a circle, so you have to be, your velocity is changing towards the inside of the turn, which means that you're accelerating which means by Newton's second law, a force must be acting on you. But what force is acting on you to get you to turn? Well, it's the wheels are exerting a force. The road is exerting a force on your wheels, both through friction. So if you're on an icy road, you won't be able to turn, right? It'll just slide off. But also, you'll notice, if you look carefully, that whenever you're on a highway on-ramp, it's at an angle, at an incline like this, to help push your car in the direction that you need to accelerate towards the inside of the curve. So force pushing this way on your car, allowing it to accelerate inward in order for you to change your velocity as you're going around highway on-ramp. So here's some examples. Okay, is a net force acting on when your car is coming to a stop? Yes, your velocity is changing, right? You're slowing down, so a force must be acting on you. What if you're speeding up? Yes, a force must be acting on you because your velocity is changing. If you're at an elevator moving at constant speed, is a force acting on you? No, not a net force. In total, there's no force acting on you because you're not accelerating. You're at constant speed and velocity. Good. If you're going around a curve on a bicycle, yes, you're curving, so you must be accelerating. So your velocity is changing. So a force must be acting on you. If you're a moon orbiting Jupiter, right? We don't have to think too hard about this because Newton's law says that yes, there must be a net force acting on a moon orbiting Jupiter because it's moving in a circle. It is, its velocity is changing, so it's accelerating. Therefore, a force must be acting on it. It turns out that's the gravitational force, which causes the moon to not just fly off, it causes it to keep turning towards Jupiter, so it orbits. Okay. I said that, so remember F equals ma, right? But suppose mass is constant, right? Because it's possible mass can change, but normally mass is constant. So, I mean, mass can change in that, if you're on a boat and you start bailing water overboard, your mass is changing, right? Otherwise it wouldn't change. But so if your mass is constant and you have a net force acting on something, that will cause a change in what? Well, it causes an acceleration. It doesn't cause a change in acceleration, it causes an acceleration. And an acceleration is a change in velocity. This is kind of a tricky one, right? You might think, oh, there's a net force, so acceleration. Well, it causes a change in velocity. Here's a question. Putting what we've talked about so far. All right, so it's long. So if a constant net force is acting on an object, constant net force. While the force is applied, what is true? So you do have a force, it's constant force. What's happening?
No change. Maybe this one. No change.
Maybe 10 more seconds. Okay. All right. This one's tough. All right, we're gonna have to talk about this one in some some care. So the majority of people said B and C, which is not correct. The second most people said A, which is also not correct. The answer is B, the object's momentum changes. So let's talk about this. So you have a constant force. So the force is constant. Net force causes then a constant acceleration. So that doesn't mean the acceleration changes. So the acceleration is constant. Okay, that's not true. But if it's accelerating, its velocity is changing. So it can't have a constant velocity, right? Its velocity is changing. Okay. The mass of the object isn't changing. That's not what Newton's second law says. So a lot of people said B and C, but remember the object's acceleration is not changing. It's a constant force. The one thing that is happening is its velocity is changing. And remember, if velocity is changing, since momentum is just mass times velocity, the momentum must be changing. Okay. So this one's a little tricky, but keep in mind, it might be on a quiz. Any questions so far? All right. So in summary, Newton's second law of motion states what? The acceleration of an object depends on its force acting on it and its mass. Specifically, it's equal to the net force acting on it divided by its mass. Okay. Let me say net force because you can have multiple forces tugging on something, but on net, you sum them all up. There's a net force, you divide by the mass, you get the acceleration. In other words, more mass accelerates less. Less mass accelerates more for a given force. Okay, Newton's third law is the law of action-reaction. For every force, there's always an equal and opposite force. I can't exert a force on something without it exerting an equal and opposite force back on me. So a good example of combining this force, say, with Newton's second law, like thinking about them both at the same time, is to think about what might sound like a paradox, right? Okay, the Earth is exerting a force on me, so it's pulling me towards the Earth. You're telling me that I exert an equal and opposite force back on the Earth? Really? Yes, I do. But why then does it seem like I'm attracted to the Earth, but the Earth isn't attracted to me? Well, that's because of Newton's second law. So if we both exert an equal and opposite force on each other, but the Earth has a much larger mass. So F equals ma. For that force, the Earth has a huge mass, so it accelerates toward me just a tiny, tiny bit. But I have a much smaller mass, so given the same force, I accelerate towards the Earth. Okay. So every action has an equal and opposite reaction. If if you get in a car collision, small car exerts the same force on the large car as the large car exerts on the small car. They both exert the same force on each other. But which one's safer? Well, it's safer to be in the big car. Why? Because it accelerates less, because it has a larger mass. So same force on each other, but the big car doesn't accelerate. It kind of just keeps going, like a train, right? But if your fly hits by a train, they exert the same force on each other, but one accelerates much more, which is what causes damage. Okay, so in summary of Newton's contribution, he discovered the laws of motion governing all objects in the universe and gravitation. And together, Moon orbits the Earth orbits the Sun, all other planets orbit the Sun, comets, debris, asteroids, all sorts of things we talk about orbit the Sun. And we can explain all sorts of things. This is extremely wide application for these very simple laws and rules. And so he realized the same laws apply everywhere, not just here on Earth. The same laws apply in outer space to the Moon, causing the Moon to orbit the Earth. It's three laws of motion. An object moves at a constant velocity, with no net forces acting. If a force does act, it accelerates. And that can mean it can speed up, slow down, turn. in proportion to its mass. Well, in inverse proportion to its mass, right? Acceleration is force over mass, or alternatively, F equals in there. Finally, for every force, there's an equal and opposite force. Okay, if you smack into something, so it's an equal and opposite force back on you. And Newton's law of universal gravitation. So I keep talking about his theory of gravity. Here it is. His theory of gravity says that every mass, bowling ball, feather, earth, sun, moon, exerts a force, and the force between any two masses is some proportionality constant called big G. It's not the same as the little g. So it's just some constant. So it's equal to some constant times one of the masses times the other mass divided by their distance squared. In other words, how big is the force? Well, it depends on multiplying the two masses together and dividing by the distance squared, meaning the further away things are from each other, the less the force of gravity. So when you get close, gravitational force increases. Those are all of Newton's laws, okay? Here's a summary of an explanation based on Newton's laws. So a rocket exerts, so what describes how a rocket takes off? Let's think about this. Well, a rocket is exerting a force on its propellant. In order to shoot propellant out the back, it's exerting a force on that propellant. So, by Newton's third law, that propellant is exerting an equal and opposite force back on the rocket. That's how rockets accelerate upward. It's by Newton's third law. Okay? It's not that mass of the rocket is changing. It's not that the air is pushing against the air or that the air is heated beneath the rocket, causing it to push back on the rocket because of the hot air. It's, well, in a way it's that, but by Newton's third law, it's that the rocket's exerting a force on the air, and then the air, by Newton's third law, has to exert an equal and opposite force back on it. Right? And this we talked about, which is that because of Newton's third law, Earth and you both exert equal and opposite forces on each other. Even though that's counterintuitive, I am exerting the exact same force on Earth that it is exerting back on me. And as we talked about, a compact car and a big truck, so you get in a collision. The force on the car, on the truck, by Newton's third law, has to be exactly equal and opposite to the force of the big truck on the small car. By Newton's second law, if you have a force, right, that causes a change in velocity, and momentum is mass times change in velocity. So the momentum transferred from the truck to the car is exactly equal and opposite to the momentum transferred from the car to the truck. But what's not true is that their changes in velocity are the same. Okay? Because of Newton's second law, if you have a larger mass for a given force, your acceleration is smaller, so the truck might not hardly feel a thing, whereas a small car will accelerate quite a bit because it has a smaller mass for the same force. Now, we've been talking about mass, right? In Newton's second law, force is mass times acceleration. Mass tells us what we call the inertia of an object. All that is kind of a colloquial way of talking about Newton's second law. Inertia means hard to move, right? More mass means for a given force, it's hard to accelerate an object. Mass ultimately is just a measure of how much matter is in an object. The more matter is in an object, the harder it is to push on it. Okay? And I want to separate that from another concept that means something different, which is weight. Weight and mass are not the same thing. While mass tells you how much matter is in an object, weight is the force you measure on a scale. Okay, you put an object on a scale, how much does it weigh? It's how much that scale reads. Okay? When an object's at rest, so you place an object on a scale at rest, This is the same as the mass of an object times the gravitational acceleration. So if you're at rest, you can calculate the weight if you know its mass and you know the acceleration. In other words, take a mass, put it on the Earth on a scale, it's going to weigh more than if you take that same mass and put it on the same scale on the moon, because the moon has less gravity. So that same mass is going to weigh less on the moon than on Earth. Okay, and this is going to be a really important concept. And one way to really understand some kind of deep things about physics is to imagine, even though the mass of an object might stay the same in all sorts of circumstances, its weight can change depending on its motion. So to help think about this, let's imagine you're in an elevator. Okay. Now, if you're in an elevator and the elevator's still, if you stand on a scale, it'll read just like it normally reads. Okay. It'll be just your usual weight. If the elevator's moving up or down at constant velocity, okay. Remember there's no force acting on an elevator on net if it's moving at a constant velocity. Scale will read exactly the same. But imagine, what if the elevator accelerates upward? Okay, so you click, you're on the first floor, you click the third floor, elevator starts accelerating upward. Okay, you feel that weight, right? You feel yourself heavier. And indeed, the scale, because the floor of the elevator is pushing up into your legs, the scale reads more while the elevator's accelerating upward. Your weight is higher. Okay? So we say your weight is higher if you're in an elevator accelerating upward. The opposite is true also. If an elevator accelerates downward, then the floor is moving out beneath you, right? Your legs are trying to press down into the scale, but the scale is moving out from under you, and you feel lighter. You weigh less. So your weight depends on whether you're accelerating upward, downward. In fact, if you extend that thought to the elevator's cable snaps, okay, and you're just falling, now the scale is falling out from under you at the same rate that you are falling out toward the scale. Okay, you're both falling at the same rate because, right, all things, no matter what their mass, fall in gravity at the same rate at 10 meters per second squared. And so what that's telling you is that if an elevator is falling, what we call free fall, you're weightless. You're not pressing at all into the scale. Your feet are trying to press into the scale, but the scale is falling out at the same rate as you are. So you are weightless if you're falling freely under gravity. So like if you're in an elevator that is falling, it'll be as though you're in outer space. You can just float around, do flips. Okay, you are literally weightless in that circumstance. Okay, so application. We're talking about an elevator, but this pertains to all sorts of things. Like if you're in a rocket, if you're in a rocket accelerating upward, you're going to be pressed back down into your seat. Your weight increases. Okay? Your mass stays the same. Your mass will always stay the same unless you're eating a bunch of candy. Maybe your mass will change, but your weight will be increasing due to the acceleration upward. Okay. Similarly, the difference between mass and weight. If you're on the moon, right? Assuming you didn't eat too much candy or something, if you're just on the moon, your mass is the same, but you weigh less. Okay? Because if you stand on a scale, it'll show less because there's less gravity pulling you toward the surface of the scale on the moon. Any questions so far? There are some example weights. Okay, on Earth, where gravity is about 10 meters per second squared, you weigh, of course, your normal weight. So suppose your mass is 100 kilograms, then the weight in newtons, that's the scientific units of weight, newtons are 981. So we can just say that's 100% of your weight on the Earth. But on Mars, for example, Mars, the gravity is less because Mars is smaller than Earth. Okay. On Mars, you will weigh 39% of what you weigh on Earth. That's because if your mass is the same, acceleration on Mars is 39% the acceleration on Earth. The moon is even less. The moon is smaller than Mars. You would weigh 17% of what you weigh here on Earth on the moon. That's why, of course, if you're on the moon, you'll jump really high, right? You'll just weigh less. It's hard for the literal astronauts on the moon to jump very high because they're weighed down by really, really heavy suits, so they can't bend their knees and jump very high. But still, they kind of jump higher than normal. Jupiter is the opposite. Jupiter is very, very massive. Now, Jupiter doesn't have a solid surface. Okay, we're going to talk all about the planets in detail, but I'll tell you now, Jupiter is no solid surface. It's all clouds, at least till you get really close, deep, and the clouds turn to liquid, and so on. But there's no solid surface on Jupiter, so you can't literally stand on it. But if you could, you would weigh between 2 and 3 times what you do on Earth. The sun is even more extreme. The sun also, you can't stand on the surface of the sun. Besides being burnt up, it also doesn't have a solid surface. You'd weigh almost 30 times more on the sun because the gravity is so much stronger on the sun. Now, there's a wonderful application of all these ideas, which is, why are you weightless in space? It's not because you're far away from the Earth and suddenly gravity disappears. In fact, right here, this is exaggerated, right? If this is the surface of the Earth, astronauts in space are just barely above the surface of the Earth. They're not very far away from the surface of the Earth at all. Gravity is about the exact same when astronauts are orbiting. So why are they weightless? Well, this is just an application of this, what we just described. Like if you're in an elevator, and it's free falling, you are weightless because as you fall, the scale is falling too at the same rate. Well, this is exactly the same as what's happening when you're in orbit around the Earth. So imagine, here's the elevator. I mean, it's a rocket in this case, but it's just falling straight towards the Earth. Then you're in free fall. The scale is falling with you, so you're weightless. But in a rocket, of course, we give it a horizontal velocity too. In other words, it fires its thrusters this way, so it starts moving this way in addition to fall. But it's still falling towards the Earth at exactly the same rate. You haven't changed that. It's just additionally, as it falls, it's moving this way, as though you're in an elevator. It's moving this way as it's falling. So you're still weightless. And in a rocket, it just the way you get into orbit is you fire your thrusters enough that you get enough sideways velocity that even though you're still falling towards the Earth at the same rate, so you're still weightless, eventually you're going so fast that because the Earth is round, its surface curves away under you, beneath your feet. So you're falling towards the Earth, but eventually you're going so fast that you started to fall towards the Earth, and suddenly the Earth has already curved away under you. Okay? And eventually you go fast enough that every time you fall 100 miles towards the Earth is curved away 100 miles away from you, and so on. So you just keep falling towards the Earth, and by the time you get to the other side of the Earth, you just keep falling towards the Earth. You try to fall towards the Earth again, but by the time you get over here, you've again just fallen to the other side of the Earth. So an object in orbit around the Earth is literally just freely falling towards the Earth the whole time. It's just you're going fast enough that as you fall towards the Earth is literally curving out from underneath your feet. So this is kind of a little bit of a hard concept to get your mind around. So I want you to ask questions if you don't quite get it. But it's a really cool concept. It explains why, if you're in orbit, you are literally weightless. And it's the same concept, by the way. You can make someone weightless in an airplane. They do this to train astronauts. It's called the vomit comet. That's their name for it, because people tend to vomit when they're on it. But it's an airplane that can fly so that it goes up and then it starts to let everyone free fall for a few minutes. So it kind of starts flying downwards so that everyone's free falling before it eventually has to start back up. And then it's the opposite. Then you're pressed into your seats at extra weight. Then it goes up and gives you another few more minutes of free fall where everyone's weightless for a couple minutes. Or of course, if you go skydiving, it's another case where you'll be weightless for a little bit before you open up your parachute. Any questions about any of these topics so far? All right, so let's see, we're making good time. So we're about halfway through this lecture, but I'll keep going some before letting you go, maybe a little early today. So one of the beautiful things in physics is that a lot of the what seems complicated about how do you predict what's going to happen using all of these Newton's laws actually is a lot simpler than you'd think. This is due to what are called conservation laws. For example, momentum, as we'll talk about, is conserved. So what that means is that you don't have to do any calculations. If you know what the momentum beforehand, no matter what happens, it's going to be the same at the end. So this actually makes things really easy and kind of beautiful, and they help explain things about orbits, for example. So let's talk a little bit about momentum conservation first, and then energy conservation. So momentum, remember, is mass times velocity. If you know an object's mass and its velocity, then you know its momentum. So for a given velocity, if you give something more mass, then it'll have more momentum, or smaller mass but a higher velocity can have a higher momentum. But the momentum doesn't change unless you act on something with a force. Okay, remember that. There's another type of momentum called angular momentum that is the same idea as momentum, but it has to do with rotation instead of what we call linear movement. Okay, and that's given by the product of an object's mass, its velocity, and its distance from the center of rotation. Okay? So say you have the Earth orbiting the sun. Okay, it has some angular momentum that's proportionate to its mass, its velocity, and how far it is from the center of rotation. Okay, and that doesn't change unless it's acted on by a twisting force. So if you twist something, that's called a torque in physics, and that can cause a change in angular momentum. And then the third really important conservation law is conservation of energy. So we'll talk about this. The energy is just some number that you can calculate that always stays constant, it never changes. And that's incredibly useful. So angular momentum, how does this help us with orbits, like say the Earth around the sun? Well, remember, an angular momentum does not change unless you exert a twisting force on something. So say the Earth orbiting the sun. Well, the sun exerts gravitational force, which points inward, causes the Earth to try to go towards the sun. It's not a twisting force. Okay? A twisting force would have to move the Earth around the sun. So there's no twisting force between the Earth and the sun. So the angular momentum of the Earth around the sun is always constant. That's incredibly useful. It is in fact the origin of Kepler's second law. Okay? Kepler's second law told us that if you're in an elliptical orbit and you're far away, say, from the sun, you're going to be going slower. But you get closer to the sun, you're going to whip around it faster.
Can you
Newton showed that this is a result
tell
of
your little
conservation
friend to come here
angular
with
momentum.
his iPad,
Angular momentum
please?
is mass times distance times velocity. And if that's always the same and your mass is not changing, then if you have a larger distance,
Now,
so you're over here, then the velocity has to be smaller. If you have a smaller distance, the velocity has to be higher. In other words, if you're far away in your orbit, you go slow, and you whip around close to the sun, you're going faster. That's just a nice application of conservation of angular momentum.
那个 friend 有個咪電話 Can you give me a friend?
And you've seen examples of conservation momentum many times in
You
your
go
life.
iPad again.
A figure skater,
The
for
same
example,
thing.
twirling around, starts out with some angular momentum, but if her arms are out, that means, so this R here is large, okay? But if she pulls her arms in, angular momentum is conserved. Angular momentum is not changing, but if the R gets smaller, the velocity has to increase. So if you're spinning and you pull your arms inward, you spin faster because you have the same angular momentum, but the R has gotten smaller, the radius has gotten smaller, so the velocity has gotten higher. And then if you pull your arms out again, you slow down. I do this all the time in my office chair. I like to spin around, keep my legs out and my hands out, and then I pull them in and then I go faster. That's just conservation of angular momentum. Now, energy is probably the most important and useful of the conservation laws. And it's kind of mind-blowing how many things in the world are all just examples of different forms of energy. So we'll see that energy can convert between different types, but it's always conserved in total. You can have motion energy, which we call kinetic energy. So if a rocket ship is flying, it has kinetic energy. Another type is called potential energy or stored energy. If I take a bowling ball up a ladder and hold it there, it doesn't have kinetic energy, it has potential or stored energy. If I let the bowling ball go, it'll crash down to the floor and it'll gain kinetic energy, okay, at the expense of its potential energy going away. So that's already an example of energy being conserved. Okay, you take potential energy,
Did he
no
go?
kinetic, let go. The potential energy goes away, but the kinetic
Did he
energy
know how to go?
increases and speeds up.
How to go?
There's also stored energy, like in
You
calories.
know how to
okay?
go?
That's an example
How?
of stored energy locked in these
Bring him
spring-like
here with the
bonds,
iPad on.
molecules. And when you eat calories, your body can liberate,
Are you sure he does?
Yeah. Turn that energy into a different form of energy that allows your muscles to contract. Okay? There's light energy, so energy through light, like
Come here.
the sun. Another type of energy. Now, all of these can convert between one another. So I'll end here, which is to
You with the same lady as Sophie?
explain this wonderful unificatory concept, which is that for hundreds of years,
What
no one
class?
had any idea,
You don't know no
no one had
class?
any idea what heat was or temperature was.
Come
right?
here,
Some things
you.
feel hot, some things feel cold. What on earth was that? And for a while, they thought that was some new special property of the universe. Hot and
Come
cold.
here.
Last couple hundred years, we understand that higher temperatures just correspond to higher kinetic energy. In other words, we understand everything to be made of these tiny atoms that are vibrating and knocking into each other. And if we give them more kinetic energy individually, they knock into each other harder and faster. And that corresponds to a higher temperature. That tells us all sorts of things. It tells us if we have little organisms like bacteria in something, and we raise the temperature, that means that all of the atoms are knocking into each other faster and harder to the point that eventually it tears the bacteria apart. Right? That's called sterilization. Right? That's why you get burned, right? You get touch something too hot. Literally, the atoms are frothing and knocking around really fast. So it starts to destroy the atoms in your finger. In fact, you can figure out a tremendous number of things just from this picture. You understand that, right? If you heat up the air in a balloon, the balloon expands. Why? Because the atoms in the air are knocking harder against the walls of the balloon. So the balloon gets hotter and it expands. If you cool down the balloon, it shrinks. So I'll let you think about that a little bit. We'll come back to this next time. I'll let you go a little early today. And we'll come back and talk a little bit more about all of these different types of energy that allow us to understand the world, actually. All these different complicated phenomena in terms of just a couple of very simple assumptions about the fact that the world is made up of just these little atoms that can be moving faster or slower. Are there any questions about any of the subjects we talked about? All right, if not, I will see you on Monday. Thank you.
Thank you. Thank you. Thank you.